This is a recording of the talk given to Headingley Cafe Scientifique on the 13th of October 2025 by Ben Kew. The talk was called Taste of Tomorrow, Unravelling Mouthfeel for the Future of Sustainable Healthy Foods.
This is a bit of my kind of history, very quickly. So I actually started my interest in food being a chef. I never really thought about going to university when I was younger. But then I discovered an amazing subject. There is such thing as food science. There is a degree called food science. It's the best degree, but that's slightly biased. And then after I did my food science degree, I did my PhD. So specifically, it was more about something called food colloids, which is actually how foods exist in the food composition. And I looked at sort of specifically plant proteins, alternative proteins, the nano to macro scale interactions in the mouth when you eat them. And then now I'm a full-time sort of food researcher, and I specialise now in a lot of sensory science. And essentially my goal is to kind of improve the health and the taste or the feeling aspects of plant protein in food use. So it's worth also mentioning that I've had the amazing opportunity to travel kind of around the world, and I've worked in all sorts of different places. So I did some work in Canada, in Wageningen University in Netherlands, but primarily all my work is in Leeds. You may have noticed this brand here, Instant Smoothies. I just finished a project with them last year, looking at how we can incorporate plant proteins into smoothies. You won't be seeing them very soon because they don't work too well in a smoothie. It's also worth mentioning as well, I've managed to get publication in Nature Communications. I've got a patent, which then led out into a spin-out company called Microlub. Co-founder of Microlub, which is very cool. And this all comes from understanding food science and mouthfeel. So I'll begin by explaining what is food science. So if you do a Google image, you'll see some interesting images like this. We very rarely even look at actual whole foods, and you wouldn't see them in a lab like this. This is very messy, chaotic. We very much look at the structures, the ingredients of foods, often, most of the time. So what I like to explain what is food science, it's like a mixture of chemistry, physics, biology, sensory psychology, maths. Essentially, I can keep going on and on. Food science is everything. Food science and food is all the scientific disciplines. So these are just some example things. I won't go through all of them, but for instance, you've got nutrition, food structure, you've got how the cooking, how that influences flavour, taste, nutrition. There's a ton of maths and statistics and physics in food, and of course there's sensory science as well when you eat food, of course. So specifically, what I look at and what my research is all about. So what I like to do is look at both what goes on and what I can measure in the lab, and how that compares to real life. So in the lab, I would look at, for instance, the size, absorption, tribology, rheology. This is from the nanometer to the millimeter scale of physical food interactions when you consume in the mouth. So these are just kind of the techniques that I use to explore that. But on the other side, I also look at the sensory aspects as well. So I do some neural imaging. I look at how food interacts with saliva, which is very important, and also sensory, actually measuring people's ratings as well of sensory. And as I said, I like to relate them, and with relating them, I'm aiming to kind of improve and kind of even predict how food interacts in the mouth. Can we kind of predict essentially food texture, which is very important aside from taste and flavour. And again, these are my kind of goals, so reducing fat, sugar, salt in plant protein foods and improving the taste and sensory and sustainability aspects of the plant protein food. But for now, I'm going to talk specifically about tribology, which is it's a very unique niche to me, and I'll explain what that is. So what is tribology? It's a study of friction, wear, and lubrication. So historically, we've been researching tribology for many thousands of years. It started with building the pyramids, altering the friction of sand to be able to produce these amazing structures. I'm sure we've all probably driven or we have cars. There's a ton of tribology in making sure those gears last and there isn't wear, and there's all sorts of frictional elements in that. We've also got biotribology, which is to do with for instance, cartilage and the lubrication of joints. And if that fails, then we have things such as hip issues, where you need hip replacements. So people study tribology in lots of different areas, but only very recently, in the past couple of decades, it's been applied to food. And so this is what I study, oral tribology or food tribology. And this is just a bit of random equipment in the lab. This is probably the most technical slide ever, but I've tried to make it as user-friendly as possible. Essentially, a typical experiment of how we measure friction of food is I got this device. The most important thing is that we've got these two surfaces. We've got a glass and we've got this PMS, so that's basically rubber. And essentially these come together, and what we have is we've got the food solution in there. And essentially we're measuring this food solution, this yellow solution. Now, glass and rubber, we assume that's the mouth, because historically that's all we've had. I'll talk in a bit about biomimetic tongue surfaces, which I actually use. But essentially, this is what I've done a lot of data on. And what we kind of get is we can kind of plot friction curves of different foods. So red would be a high friction food. So I hope you can see on the y-axis, you've got this up here is higher and this is lower. So this, for instance, could be, and let's just say ice cream. It's a low friction food. But we've got these high friction foods as well. And that's typically actually these plant-based foods, so plant protein foods. And how does this relate to when we actually eat food? So I'll just skip over this because it's a bit technical. But what we can actually do is we can look at the friction at different sections on this reading that we've got from each food. And this actually relates to different structures of when we eat food. I like to think of this in terms of cheese. So when you put cheese in the mouth, the first thing you get is thickness, viscosity. As you're chewing, you're getting oil released, and you actually get tribology, which is a sort of like a reduction in friction and interactions with saliva. And we kind of measure all of that in this area here. That's not too important, so I won't go too much about this. But essentially, from producing these friction graphs, these friction curves of food, we can actually correlate these to certain sensory attributes. So for instance, down here, we can tell if something is thick or if it is thin. Here we can tell if something is slippery, creamy, fatty, but also if it's rough or dry or astringent. So essentially, if there's a key takeaway from this, is that we can start to predict certain sensory attributes which are really important for our liking of food. And again, we've actually developed these biomimetic tongue surfaces, and I've got some with me today, so you can pass them around. I'll bring those out later. But essentially, what we can do is replace this setup and start to incorporate real life kind of biomimetic tongue, real kind of surfaces. Cool. So yeah, that's a brief introduction to tribology. So what we'll do today is we're going to explore taste and flavour first. Then we're going to talk about texture, because these are all very different things. Then we're going to have a look into how this understanding tribology and texture influences and is kind of is important for my research. We're going to then explore why do we kind of have these tastes and preferences for food, and then finally we're going to look at what the future of food may look like. So we're going to start with taste and flavour. In a minute, but not yet, I'll allow you to, you'll be able to taste the first sample, essentially. So it's worth saying that taste and flavour are not actually the same thing. People tend to get those confused. So we're going to go through the basics of what is taste. So taste is purely what you detect on your tongue alone. You've got all of these taste pores, and what you can taste is a few things. So sour, salty, bitter, sweet, umami. These are the common ones you've heard about. There's a lot of argument about, you can actually taste metallic, you can taste heat, from chili. So that is taste. And to debunk a common myth, you don't taste food in certain areas of the tongue, you actually detect them all over. So that's a bit of a myth, the fact that you can taste sweet in some areas and salty in other areas. Because yeah, these are all over the place and you detect it all over. Now it's worth knowing that you've got 2,000 to 10,000 of these taste buds. that is actually quite a large range. If you notice, like, so one person could have 5 times as many taste buds as another person. This all depends primarily, one of them is age, but this actually also depends on your diet as well. So if you consume a lot of fat and salt and sugar, very high, kind of like these more unhealthy based foods, your taste buds actually reduce, and you actually become undersensitized to fat, sugar, and salt. So you have an increased preference for these fatty, unhealthy foods. However, if you didn't consume these foods for a while, eventually your taste buds will increase, so that when it comes to eating, for instance, a cake again, it will be almost like too aggressive, it'll be too strong, and you won't actually like that food anymore. Essentially, your taste buds are replaced approximately 10 to 14 days. So let's just say you cut out sugar and fat from your diet. In 2 weeks' time, your perception of sweetness will be very heightened. Same for fat as well. To the point where you actually, when you go back to trying these foods, you might not even like them, and you might actually just prefer, lower sweet foods. For instance, an apple might taste just as sweet as, I don't know, the cake 2 weeks ago. So this is a really interesting bit of research. So, without further ado, we'll do time to taste. So, to isolate taste, what we're going to do is we're actually going to pinch our nose while we consume these solutions, because your nose actually detects aroma and detects flavour. What your tongue does, it detects the taste. So feel free to have sample. So this is sample number 1. If you don't want to pinch your nose, you don't have to. Essentially, it's a chocolate flavoured drink. So hopefully it won't be too horrible. But we're going to try and really think about what is taste and what is flavour and why they are different. So what you're thinking about is, what do you detect on the tongue? Is it salty? Is it sour? Bitter? Sweet? Or heat? Probably not heat, but so you'll probably detect sweet.
Yeah.
Yeah, that's right. There we are. That's all there is to it.
Also sour.
Okay, good. Okay, so potentially sour. I mean, it is chocolate flavouring in a. But to be honest, maybe there's so much in there that you get a crossover between sweet and sour, which is quite interesting. But essentially, that's teaching you that is taste: sour, salty, bitter, sweet, sour. Now, as you probably noticed, when you release from your nose, you're able to then detect flavour, which you'll get as chocolate. So flavour is different to taste. Flavour is essentially aroma, because essentially what happens is, when you consume food, you've got this flow into your nose, and as you're breathing out, as you're consuming the food, you have all of these volatile aromatic compounds interacting with the nose, these olfactory cells. And again, while you have maybe 2 to 10,000 taste buds, you've got about 12 million of these olfactory cells. So that is super, super sensitive, and it's why you can differentiate so much between, for instance, a strawberry sweet versus a cola sweet. They're both sweet, but those differences in flavours are noticeable, because you've got this extreme sensitivity, and extremely complex as well. And of course, you can think of other animals like dogs, which have 10, 20 times as much. It's kind of mind-blowing how they would experience the smells around them and their tastes. So yeah, these are kind of the volatile compounds in foods. Again, I won't go too much into it, but as you say, it's a mixture of these volatiles in foods which really allow us to know what is cola flavour, what is strawberry flavour. And then in terms of so what I've got here is a flavouring. If we compare it to a whole food, you'll notice flavouring is never quite really the same as a whole food. One of them is because in a whole food you have about 1,000 different compounds all in your nose at the same time, and it almost smooths out the kind of the aromas and the flavours. While with an actual flavouring, which is like an artificial flavouring, they only take about 20 of the main components, but it's always quite harsh and rough and aggressive and like artificial. Although these have about 20 different flavours, the other 980 actually round off flavours. That's why these taste a bit artificial. However, you've also got the importance of texture as well. So this is where we move on to texture. So with this, we've got another example, which is chocolate. And again, I'll let you know when you can eat your chocolate. Not quite yet. Hopefully, if you haven't already. So how you detect texture is that you've got these mechanical receptors, and you can taste things, as I said, from nanometer to the millimeter scale. So in the millimeter scale, we've got things such as viscosity. You know, like a smoothie is thick, tap water is thin. You can detect that in the mouth. Now you've also got things on the surface as well, and this is the tribology. So this is at the nanometer to the micrometer level. What goes on with food in the interaction with saliva and the surfaces in your mouth. And you've got things such as high friction foods and low friction foods. So high friction foods would be dry, rough, off mouthfeel, while these lower friction foods would be smooth and creamy. And obviously, I hope you can start to realise that you'll probably prefer these lower friction foods rather than these higher friction foods. It's just exactly what I can measure in the lab as well. What I like to explain, so what we've got here is we've got low friction, high friction. The easiest way to think about this is actually milk. So if you've got skimmed milk versus whole milk or cream, you can definitely tell there's a difference. And a lot of that is actually the creaminess, and that's actually to do with the friction. As I said, lower friction at this end with the high fat. We also, a lot of the favourite foods we love as well, very juicy, very fatty, again, lower friction. However, in the other side, we've got some of these foods which we don't necessarily like as much or least preferred, and these are actually generally higher friction. So these have certain compounds which bind to saliva that cause dryness, and that's why we kind of love these rather than these. And again, this isn't taste, this isn't flavour, that is important, but also this needs to be appreciated. It's that the mouthfeel, the nanometer scale, what happens at the surface of the mouth. And this is the same issue with proteins as well. So meat and dairy proteins are lower friction, while you have a lot of these plant proteins which are actually high friction. They're quite dry, they're quite rough. That's why there's a lot of issues with trying to hide and mask these by adding lots of fat, sugar and salt currently to the foods to try and hide these rather than these. So there's a lot of issues. But if we can solve this and bring this down to here, then technically we're thinking you don't need that high fat, sugar and salt, which is what I'm working on as well. So it's estimated that actually 75% of why we love food and why we don't like a food might be to do with texture. So a classic example is like mushrooms. So actually, if you had that mushroom flavour, we actually love that flavour and that taste in food. It complements a lot of foods, but it's that slimy texture we don't like. And actually, there needs to be this a larger appreciation into the texture of foods, specifically kind of the tribology, which is these surface interactions. But of course, you know, there are certain tastes and flavours we don't like as well. But there's a lot of preference in that texture, which people do forget. So let's have a think about the texture of chocolate. So if we look at the chocolate structure, essentially what we have is a lot of it's fat, and floating around in that fat you've got sugar, you've got cocoa and milk powder. And that's essentially, very simply, what chocolate is. So this is the point where you are allowed to have your chocolate now. As you're as we're gonna try and think about what's going on in the texture of chocolate, which makes it so nice.
Chocolate's not just a monolithic entity. There's a very different mouthfeel from a high quality single varietal chocolate than there is from.
You've got a range, yeah. It's like Galaxy as well. Galaxy's very, very unique mouthfeel. This tends to be to do with particle sizes, yeah. So that's very much, yeah, very important structure and texture relationship. Cool. So what you may notice is, well, I don't know, might be a bit warm in here, I'm not sure, but the first thing you get is a snap, which is texture, which we love in chocolate. The next thing you get is actually an endothermic reaction. So what you'll notice is your tongue is cooling, because what is happening is you're having a phase transition from solid to liquid that takes energy. So it will take that energy, that heat energy from your tongue. So your tongue actually cools down, which is very unique to chocolate. You don't see many examples in food in that. Again, this contributes to why we love chocolate. Another thing we get is this. So what is actually happening? So this is a PhD student in the lab, and this here is basically essentially sugar crystals in chocolate, and this is saliva. So what we're seeing is we're seeing explosions of sugar, and what that's doing is you've got all these little particles, and that is helping the flavour release. So it's almost like these explosions of flavour that's coming out as saliva is interacting with chocolate. So we have this as well, so you have an explosion of this flavour release. You've also got a viscosity decrease. This is to do with the rheology, the millimetre phase. And then you've got this surface interaction, so the tribology, which is reducing the friction. So yeah, it's very complex, but yeah, the texture of chocolate is whole research groups dedicated just for that. And it's very important. It's why we love chocolate. And also, Leeds University was in, so our department got quite, got some news attention over the chocolate texture that we examined using tribology and rheology. Essentially, by understanding tribology and the texture, we're actually able to kind of predict, and we're able to design like a potential low-fat chocolate that feels the same, just by understanding those interactions with saliva. So I'm not sure if there's people who are actually working on low-fat chocolate incorporating this technology, but essentially this just comes to say the importance of understanding texture and the design of more kind of healthier foods. Cool, so that's all great. So we've learned a lot about the friction of really nice foods, so chocolate. Now we're going to talk a bit into the opposite. So we're going to be looking at how I look at friction and mouthfeel in plant protein foods. So, as you may have noticed, some of these foods, they're not that nice. They often use fat, sugar and soda to mask poor tasting, so there's nutritional as well as sensory issues with these currently. And yeah, if I just throw some of these are very common attributes that we get with kind of meat. And then these are some of the ones we get with some of these plant-based proteins. So I think one of the common ones is dry or enough flavour, off mouthfeel. And actually, a very key thing and a very unique issue to plant proteins is something called astringency. Has anyone ever heard of that before? So it's kind of almost like a dryness of the mouth. It's a very unique feeling in the mouth, which you will experience in sample 3.
Have you tried eating a raw banana?
That's, yeah, probably not very nice. But
I think that's better.
It could be bitter as well. And it could be bitter or astringent. Probably a bit of both, yeah. And yeah, you get this issue with plant protein. You don't get this with meat. You don't get this with milk protein, which is a big barrier to overcome. And this is a friction issue. It's not necessarily, it's very highly debated if it's a taste, but it's actually going more towards it's actually a textural issue.
Interesting, because some honeys are noticeably astringent, even though they're liquid.
Yeah.
Which seems a little bit strange if it's a friction issue.
So that liquid is a macro scale issue. So if it's thick or thin, that's macro scale. While the nanoscale, the individual particles in that liquid, that's astringency. So it's kind of different length scales.
Right, okay.
So what you've got in your honey might be compounds which are very small and they're binding and interacting, rather than the whole macro property of that solution itself. So I've actually done some research into astringency in neuroscience. So this is a very cool cap. And essentially what it does is it kind of looks kind of scary, like it's frying my brain. But essentially it just shines a red light in your brain and you're able to measure essentially blood flow in the brain. So you can get response of brain in certain areas essentially. I did a whole project, there's actually, I've got a paper coming out actually very shortly on this. So essentially I tried to investigate astringency in the brain as well as doing sensory science, and what we see is very much a physical issue. So when you consume these plant proteins, what is happening is as you eat them, you've got saliva on your tongue, it binds to the saliva, it precipitates, it dries your mouth, and these plant proteins further bind to the actual tissues of your tongue as well. And this generates a unique astringency response. Now, this response is not flavour, it's not taste. I controlled for this in a recent experiment, and your brain specifically can detect astringency, and why that is I'll go into later, but it's an evolutionary sort of thing. So now we can try astringency. So I'll tell you what sample 3 is. It's just green tea, but this is a really nice way to actually, how you can actually feel astringency and what it is. If you're interested, you can, but you know now what's going to happen, so you might not want to drink it. Probably no. Soy sauce is very salty. It's probably a bit of a confusion between that taste and this. So basically, if you did want to drink the green tea, what is essentially happening is your mouth is coated by saliva, a very thin amount. Without that saliva, your mouth is extremely rough. Actually, you wouldn't be able to talk, you wouldn't be able to eat, you wouldn't be able to swallow. So saliva is extremely important in your mouth. And what is actually happening is, with the sample that you've got, the green tea, but also these plant proteins, it's binding to saliva, causing salivary loss and a very unique astringent perception. And again, that is tribology. This is surface. What's going on at the surfaces? Yeah.
There's also bitterness there.
It could, yeah. So there's a very unique. There's a very strict protocol on what is bitterness and what is astringency. You will naturally have some of them together, but the green tea is primarily astringent, but also bitter. It's debated. So we can discuss in a bit.
It's nice to know what that feel is now. You know, that really good green tea normally got that feel.
That's it. Yeah. This is it. Yeah. But we actually quite like it. So, for instance, in red wine, it's what we like about red wine. It dries our mouths, and then we actually have cheese that restores the lubrication, and that balance of high friction, low friction, high friction as you're eating cheese and wine is what we love about those combinations. But what you don't want is this in a sausage or a burger. And that's why we don't want this in sort of these plant-based proteins.
Is that why it's called dry wine? Is that why wine is
kind of dry, yeah.
Well,
Well, that's to do with the sugar content, but it's probably, you get it more with red wine. Red wine is the astringent, yeah. Cool. So now we're going to move on to, by understanding what we love about friction, what we hate about friction, how can we design kind of healthier and better foods? So can this be resolved without adding fat or other ingredients to kind of hide these and mask these, which is what the food industry is doing at the moment. So we know we can actually design cool food by understanding this issue. So now we're thinking of it in terms of plant-based solution. So actually, here is where I'm going to pass around these tongs if you want to. So people are amazed by them or they're creeped out by them. So I won't force you to feel them if you don't want to. But I will just leave a couple on here so you can pass them down the table. But these are genuinely these haven't been in the lab. So these are safe. So I could genuinely put. I could genuinely put food solutions on these, and these are actually what I'm doing to measure friction. There was a whole 3 or 4 years developing these surfaces, because obviously glass is not what we have in our mouth. We have something like that. But I won't go too much into it, but feel free to grab me after if you've got more questions on this. So to resolve this problem, essentially, it's a simple question. How do we block this interaction with saliva? Actually, we've been able to take plant proteins and do a physical processing method, which is actually quite straightforward. So almost coat plant proteins in like a gel or a liquid, so it doesn't interact with saliva. It's called this kind of leads to these very, very slippery foods, which are actually 99% water and 1% plant protein. So it's called microgelation. So this is literally the process. So what you take is proteins, you gel them, and then you homogenize them and break them down. This might look kind of scary and artificial, but it's actually quite similar to how you would make, for instance, a jelly at home. So you would take, for instance, your powder, you would heat it, for instance, put it in boiling water, it would turn into a solid, and then you'd essentially break it down. So we can kind of do that with plant proteins. And then what you actually have is these structures, which are the protein, but they're actually, they've got this like gel around them that hide and stop that interaction. What's amazing about these microgels, is what they're called, is that they're called ultra lubricating foods. So they're very, very low friction. So we can convert this here, this plant protein here, down to here. So it's an order of magnitude improvement. What's even more phenomenal is if you compare it to single cream, which is 20% fat, you've actually got these microgels which are even more better than the single cream. So we've got these microgels which are very, very creamy, very fatty, yet they're mostly water. So I hope you can kind of get where I'm coming with this, but essentially you've got something which is 8 calories versus 200 calories, and they feel the same. They feel fatty.
So what you're saying is that your ultra processing of this food, using that term advisedly,
yes,
is improving mouthfeel of healthy, a healthier diet.
Yeah. So this is the misconception. So ultra-processed food is something called an umbrella term. Essentially, there's foods which are classed as ultra-processed which are extremely healthy, and some which are not. And actually, if you look at the fundamental issues of what is bad about ultra-processed food, it tends to be food which are high fat, sugar, salt, low fiber. That's actually the message. It's not ultra-processed. It's to do with the nutritional composition. But again, maybe that will be a heated debate later. I'll quickly get through my slides. Okay. So what we've actually been able to do with these microgels is take, for instance, a sausage, which was 200 calories, or a piece of cheese that was 400 calories, reduce it to even a third, and people actually can't tell the difference. So we've ran these in trials. People don't tell the difference. They still think it's that same fatty perception. And again, this is from understanding tribology and food science. And this technology, this microgel, is exactly what the spin-out company is. And yeah, we've been granted 3.5 million to basically do the startup. And now I think there's 8 people employed, and they're trying this technology with all sorts of food companies, trying to reduce fat, improve sort of calories in food, but also incorporate plant protein into food as well, which is very beneficial in other ways. Yeah, they have a whole website. Feel free to check them out. You can read more about it on there as well. So at this point, I'm going to do a bit of a recap. So we've talked about taste, flavour, texture. We've talked about the challenges of the unique challenges of textures, for instance, astringency, this tribology issues we have. And by understanding this food texture, we can start to develop solutions to sensory and health, which we never thought we could do before. Most of the research, most of what food industry have focused on is taste and flavour. They've neglected the physical interactions of food, which is what we're understanding now. And so it kind of opens up a whole new exciting possibility for food that can be improved in all sorts of different ways. So now I've talked about kind of the sciencey part. We're going to talk about why we taste how we do. So this is going to be a bit of fun. So we're going to go back in time. It took me a while to make this slide. So we're going back 2 million years. So this is explaining why we like what we like. Essentially, 2 million years ago, calories was life and death, full stop. Age expectancy at this time was 25 years old. So what we loved was these high fats, high sugar, high salt, high energy foods, because these were rare in abundance in the environment. And what we didn't like is we liked these more vegetable matters, which didn't have much calories, or they were poisonous, or they have very high fiber, which we can detect. Essentially, we found sweet, fatty, and salty food delicious, and these bitter, off mouthfeel, astringent foods less delicious, very fundamentally. So you've got to think, 99.5% of our entire evolutionary timeline, we've had this issue. It's only 10,000 years ago. Yeah, that sounds like a long time, but in our evolution, it's not really. We came across agriculture. We were able to reduce the fibre in food, put more carbs, protein, fat in there. Population increased massively, and life expectancy increased massively as well. So this is quite interesting because at this point, life expectancy is kind of now 73. So we actually, it's funny because we have processing to thank for this extremely improved life expectancy. However, what we have now is we've got an emphasis on healthier living. When we are older, how can we improve our lifestyles? And it's not to do with calories, it's no longer an issue. So we have a lot more other things, like we need to actually have these fibres and these less delicious foods. And those are they're becoming more of the importance for our healthy living. So we have an issue nowadays in that essentially we still have a taste for these delicious foods and these non-delicious foods. So the quote is Stone Age senses in a fast food world. And this drives a lot of issues as you probably are well aware. So it's a problem of sense. So one of the biggest issues is obesity, because we love all of these delicious foods, but they're so high calorie, and we tend to prefer those rather than sort of vegetables and fruit. And we have this low preference for plants as well. So another issue as well is the sustainability aspect as well. And eating too much animal protein and getting people to eat more plant protein, there's an emphasis on this as well, which we don't require fat, sugar and salt. I'm not going to focus on the obesity aspect because that is a whole, go on for years about the topic of that, but sustainability is what I'm going to kind of point towards now into why we should be trying to consume more plant proteins rather than animal proteins, which is what my whole topic is about. So yeah, let's jump to a taste of tomorrow. So we have issues with our senses. We love unhealthy food, and we don't love nicer, healthier food. So I just assumed that maybe in about 8,000 years' time, what we'll actually have is our taste buds will be much more sensitive to subtle flavours. So we'll actually lose our love for sweetness. We'll probably have an extreme sensitivity to sweetness. Because what will actually drive kind of unhealthy, what will drive kind of, death and evolution will be consuming less sweet foods, more fruit, more fibre, and not consuming very sweet, sugary foods. So there's going to be this, the theory is there's going to be this sensory recalibration where we actually lose our desire for fats and sweet foods, and we'll start to enjoy more of these bitter, astringent fibre foods, which are all associated with healthy aging. So it's quite interesting because we might actually get this swap around at some very, very long time. I mean, not I said 8,000 years, it might be a million years, who knows. Essentially, the point is, I don't think we can wait that long. So we're going to jump to what 2050 will be like, and this is within a short kind of lifetime, so within 25 years. Essentially, we're going to have a lot of issues and strains on the food environment that we have. So there'll be a population increase, and protein demand will double worldwide, and it will put an extreme strain on the food system. We're already seeing issues: climate change, sea levels, and less predictable crops as well. Food shortages, food running out of supermarket shelves, stuff like that. However, this all kind of depends on today and our own actions. This is just some really crazy statistics about comparing animal versus plant-based foods. So the first thing I'll say is, in all of the man-made greenhouse gas emissions, food industry is responsible for 35%, which is huge. 17% of, which is more than cars and aviation aerospace combined, which is quite mind-blowing. 17% of this is just to produce animal-based proteins. Now, what's really kind of shocking, I guess, is that even though it produces 17% of these global greenhouse gas emissions, it's actually very inefficient. So if we look at the whole global calories that's produced from this 17%, it's only 18% versus plants, which is 82%. Global protein is 40% versus plants, which is 60%. And the land use is massive when we're producing these animal proteins. Essentially, it's if we maybe reduce animal production a little bit, and you actually get a lot more space freed up for having more calories, more protein, and more land use. And less land. And the question is in 25 years' time, this will double. So can the world handle it? That's the big question. So this is just some other statistics as well. So in terms of like the CO2 produced per 100 grams of protein, with beef, it's famously the worst culprit. It's 26 times more producing CO2 than, for instance, per gram of protein than other crops. I think this is, for me personally, this is one of the most surprising and shocking statistics, is that per kilogram of beef or pork or chicken, this is the amount of total thousands of litres of water that's needed to produce this, from feeding the animal all the way to slaughter. So 15,414 litres of water, fresh water, is, well, in a way, is needed to produce this 1 kilogram of beef, which is crazy. And you may think, where is all this water coming from? A lot of the food that we consume in kind of West is from, we feed these animals with kind of imported soy, imported crops. Actually, by feeding them this, there's a lot of deforestation, which is even worse than farm. We don't really hear about it. There's this freshwater scarcity. So there's this fresh water available in parts of the world that is kind of, in a way, exported to us in the form of what we feed these animals. So we're taking fresh water from parts of the world and bringing it here, which we shouldn't be doing, ethical reasons. And also, this leads to obviously water pollution as well. So these are kind of, these are some kind of quite interesting statistics. Of course, there are specific examples where this isn't true. For instance, if you had grazing on land which you couldn't grow in, and it was local, that would be a lot less of an impact. But this is actually an average for all of the meat. So yeah, it's quite interesting. But then I say there's some hope. So again, there's a lot of research and being put out there to try and improve this. One of the biggest things to axe to kind of reduce climate change impact is through our food habits. And one of them is, and one of the biggest ones is kind of going towards more plant-based foods rather than animal-based foods. And yeah, there's all sorts of centres that have appeared in the UK in the past 2 years. So you've got this Bezos Centre for Sustainable Research and this National Alternative Protein Innovation Centre, which is based in Leeds now, and that was only been there for about a year and a half. So this is some fun slides. So I just kind of imagined what our supermarkets could look like in 25 years. So if we continued how we are today with our own consumption of kind of excessive consumption of animal proteins, what we will see is we will still see food out there, but what we might get is more products being out of stock because, I know, maybe climate change has accelerated so much that we can't get ingredients for certain foods. You'll see price rises, dramatic price rises, and I guess you'll see a lot less variety in the supermarkets that we have today. This is what, in theory, the 2050 world could look like. In the UK, I think we're already seeing it, to be honest. Like if you've looked into supermarkets, you see some foods which are out of stock, and especially fruit and vegetables as well. But this will be essentially a lot more common. However, we do switch to more sustainable food systems. What you might find is an accepting a lot more of these new proteins. And what we'll have is we'll have such a kind of a new range of products emerging from all sorts of different new proteins that we're only just discovering. So a few of them I've put in is, we'll still have the meat, that will never go away. I don't think it will ever go away, but that might just be a smaller section in the supermarket, for example. And what we might have emerging is these more plant-based alternatives, which are healthier. At the moment they're not, but they will be. And hopefully, if we can solve these sensory issues, and we'll also get all these really cool proteins emerging. So leaf proteins are a really interesting one. So even getting proteins from grass, like it's the most abundant kind of material, and they're even looking at maybe even getting proteins from there, and how can we actually incorporate those into our diets. And yeah, I think algae proteins, vegetable proteins. I put insects on there. That's still a bit of a. I think there's other ways to get protein in our diet. I don't think we need to go to insects yet. Yeah, there's going to be these new kind of proteins coming out. For instance, the spin-out microlove. These really cool kind of fat-like materials which are made of protein, plant protein. Essentially, the key message is reducing excessive animal protein consumption in developed countries and adopting more variety and increasing alternative protein foods, which are made healthier and tastier, which we hope we will get there in the end. I mean, that's kind of my job. So yeah, that's pretty much everything for today.
Well, thank you very much for that.